Today we're going to be talking about this example in which a rare disease affects 1% of the population. Now, scientists, whoever has designed a test um, for which if the person actually does not have the disease, the test correctly identifies and confirms the individual does not have a disease 99% of the time. And then in the scenario that if you do have the disease, the test identifies this outcome 95% of the time. Okay, so we have a couple of questions here. The first question is what proportion or probability has the disease and test positive? The second question is what proportion of the population tests positive just at all? And then the final question asks this: if the test is positive, what is the probability the individual has the disease? So we're going to illustrate what's called a tree diagram. And this is part of what's new. Tree diagrams are really helpful for conditional probabilities. So to get started, we're going to start with a single node, and there are two outcomes for this node. So either the individual has the disease, which is yes, or they do not have the disease, which is a good thing. Now, from here, we're going to branch out and have another two nodes. And these two nodes are going to be for the test. Okay, so we can test positive in each outcome. So if we have the disease and we test positive for the disease, that's a good thing. If we test negative and we have the disease, that's called a false negative. Okay, again, the outcomes are positive or negative. So if we don't have the disease and we test positive, that's a false positive, that's a bad thing. Or we can we can not have the disease and test negative, confirming that we don't have the disease. And that's a good thing. It means we made the right decision. Okay. So here, we're told enough information to fill out the probabilities here. So it says a rare disease affects 1% of the population. So 0.01, that's 1%, have the disease. So we're going to put 0.1 there. And 99% of the population does not. Then it says if you do not have the disease, so we're in the no group here, The test correctly identifies this outcome 99% of the time. So that means 0.99 goes here. Okay, so that's correct identification. And that means 1% of the time, 0.01, we make the wrong decision and we get a false positive. It also tells us that if you do not have the disease, the outcome identifies this. Excuse me, if you do have the disease, so we're in the yes portion, the test identifies this outcome 95% of the time. So 0.95 is here, and here we get 0.05. So all in all, pretty good results here. Okay. Now, one thing that I'd like to point out is a lot of people have trouble identifying all the probabilities here. So what was given was, for instance, this 1% that has the disease. Well, that was given in the very first sentence, and you had to infer that 99% did not have it via the complement rule. Okay. We were also given 99% test negative when they don't have the disease, and you had to infer via the complement rule that 1% had a false positive rate right there. And the similar for the upper, that it gave us this 95%, you had to infer the 5% right there. Okay. The last thing that I'll note is that everything that was just highlighted, the 95%, the 5%, this 1%, that 99, those are all conditional. So they all have the words if you're in the disease group, if you don't have the disease. So that makes all of these conditional probabilities that are displayed in this tree diagram. Okay, let's answer some of these questions. So, one thing that I'd like to write down is it asked this question in number 1. Let me change my pen here. So in number 1, it asked this question: what proportion have the disease and test positive? So this is asking probability that the disease is yes, and the test is positive. Okay. There's a keyword here which is an and. We have to use the general multiplication rule. So we're going to calculate the probability of the disease being yes. Then we're going to multiply by the probability that the test is positive given, and given has this notation of a bar, given that the individual does have the disease. And this is just going to be this 0.01 times this 0.95. And that is 0.95%. So about 1% of the population. Less than 1% of the population, right? Because 1% has it, and almost 1%, 0.95, test positive for it. Okay. And the others are given a false negative, so they're mistakenly told that they don't have the disease when in fact they do. So question 2, this asks what proportion of the population as a whole tests positive. So this is the probability the test is positive. There are 2 ways to test positive. You can have the disease and test positive, or you cannot have the disease and test positive, the latter being a false positive. So this will be positive and have the disease. So let me put yes for yes, we have the disease and the test is positive, or we cannot have the disease and we can test positive. So I've shorthanded this. With this or, because there is no intersection, we can just add them. And there's no intersection because we can't both have the disease and not have the disease at the same time. So this first one is that we have the disease and the test is positive. Well, we just calculated that. That was this 0.95%, and that's 0.0095. And that was given just by multiplying along the path to get a positive. So for this second one, the probability of no and positive, well, we can just multiply along the path to get a positive. So 0.99 times this 0.01. And when you add these two together, you're going to get 0.0194. And that's actually an equality, which is about 1.94% of the population. Okay, so about 2% of the population tests positive, and only 1%, only about 1%, 0.95 of a percent, actually have the disease. Okay, so that's a little bit alarming. And it shows us why it's alarming in this third outcome here. Okay. Just gonna delete a little bit from this diagram here. Okay. So this third one asks for this probability that we have the disease. So disease equals yes. And here I'm switching back to the longhand. So the disease is yes, given, and given is just that bar, given the test is positive. Well, this is a conditional probability. Conditional probability is calculated as follows. We calculate the probability of the intersection. So both outcomes occur. So I did that intersection, but I'm going to write it with the and. So intersections and ands are the same thing, and the test is positive, divided by the probability of the conditional, that the test is positive. Well, the test is positive. That's what was calculated in the second question. That's this 0.0194. The probability that an individual has the disease and the test is positive, that was given in the very first question, and that's 0.0095. And so when we do this, we're going to get about 48.9%. And that's pretty concerning. This says if you test positive for the disease, the probability you actually have the disease is just about a coin flip, 49%. Okay. I'll just comment that this third probability is a conditional probability. It's also an example of Bayes' theorem.